Yeah, so as mentioned by Herman, I'll be talking about productionizing a machine learning system at a large Australian telco. I am a principal machine learning engineer at a company called Simple Machines. We're a consultancy out of Australia, which is a very, very long way away from here. And we do data consulting in general. So we work on data streaming systems, we work on big data systems, machine learning systems, all this kind of stuff. I've also recently become an open source contributor to scalability, helping out on some of their analytics projects, if you've heard of it before. If not, hopefully I can talk to you about it at some time in the future. So first of all, can I just get a quick feel for the room? Who here is a data scientist? Okay, so we've got a couple. And who here is a data engineer? Okay, that's what I thought. Okay, so this talk is kind of mostly about data engineering, but for the data science process. So hopefully all of you get something out of this. So before we get into any of the details of this stuff, it helps to kind of position organisationally where the company in Australia, the telco that I'm talking about, was actually trying to end up in both its data science and its data engineering capabilities. So for its data science capabilities, they wanted mostly distributed setup. So the idea was that each one of the teams would have a set of data scientists that could work on delivering business value independent of one another. But then they wanted this kind of small centralised ability to share code and share features and all this other kind of stuff. And they wanted their data engineering team to basically be the enablers for this. So the idea was that there's a lot of common infrastructure when you build these kind of data science and machine learning projects, and they wanted that to be set in one place. But then they still wanted to be able to have engineers embedded in each of the teams for the specific stuff that they need. Now, if you think about the data science workflow from a sort of million miles away and squint a little bit, it might look something like this, where you start with a business problem, you then do some kind of data extraction, some data exploration, build some features, build a model, evaluate the output, and then obviously have this kind of feedback loop. And obviously that feedback loop can go further and further back depending on how wrong you got things. And then the model serving is the final part where you push stuff into production. Now, it can sometimes look a little bit more like this, but we'll kind of skip over that and focus on the three main areas that data engineering tend to get involved in. And that's primarily data extraction, the building of features, and model serving. Now, data extraction is effectively ETL. Conceptually, it's relatively straightforward. In practice, it can be really challenging, especially at scale. I'm not going to spend too much time on it today. What I'm going to spend most of the time on is actually the building of features, how you can centralize this and scale this up at an enterprise. So before we get to that, just a quick introduction of what machine learning actually is. There's a lot of kind of hype around it, especially around deep learning and AI and all this kind of stuff. So you might think maybe building Terminators or self-driving cars or AlphaGo super intelligent game-playing robots, but the reality of it is that most enterprises are actually doing something a little bit more mundane. They're doing stuff like this, where they want to cluster some of their data points to actually try and work out whether they are advertising towards, say, a luxury segment or knitting enthusiasts. They might be doing something like trying to predict churn of their customers, in which case they might do something like a basic classification, where they want to predict whether or not a point is going to be on either side of the line. Now, you can see here that this graph actually has these kind of question marks on each of the axes. And these are really important to understand what they are, because if we're trying to draw a line through these things to make a prediction, we need to be able to find some good lines to draw these lines on. And what they are is features. Now, a feature, the idea is that since we can't directly measure the thing we're trying to predict, say, for example, churn, we need to instead try and get some things that we can measure. And the things that we can measure might be something like, the last time since the user visited this page, tenure of the customer at the time of the particular instance, or maybe the banded volume of purchases, low, medium, or high, for example. And then the idea is that each one of these features will be tied to a specific customer and point in time, or whatever the cut of your data is. Now, features are interesting in that they can be very simple. They could be as simple as taking something from a table in another part of your business, all the way through to incredibly complex joins and aggregations that form some kind of insight into the thing you're trying to predict. And it turns out that whilst there's a lot of hype around deep learning and kind of the extent of what it can do, a majority of the performance of machine learning algorithms in the real world actually tends to come from well-engineered features. I've seen it time and time again. So absolutely try to avoid the hype when it comes to deep learning unless you're doing very specific types of things. Now, training versus scoring with features is a really important distinction. Typically, you start with training data, which is usually very big historical snapshots. The idea here is that you want to give your algorithm as many data points to understand the underlying distribution you're trying to model so that you can then make predictions in the future. But when you make the predictions, all you actually need is the tiny bit of data that describes an instance at the point in time that you want to make the prediction. So the process might look something like this. You've got some data sources somewhere in your organization, in this case the blue, yellow, and red. You've got some kind of feature logic that produces your training table, and then a label, which is what you're trying to predict. And then you do some kind of iterative training, in this case just a simple decision tree, say to predict churn or no churn. And it might decide, through feature selection and all the things you do, that it doesn't need all the features and you only end up with the red and yellow ones, for example. But then what you want to do when you put this into production is basically take the two parts of this, which is the feature logic and the actual models, and you want to take them and put them into the production setting. Now, what a lot of companies that I've been at kind of do is that they start by saying, let's just get an ad hoc version of each of these projects. We're going to get, we're going to try and solve this problem over here, this problem over here, this problem over here. And before long, they realize that they're actually doing a lot of similar stuff. A lot of the companies will realize that, for example, a lot of the infrastructure that they're using is the same. A lot of the features that they're actually building are quite similar when you're in similar domains. And so they come up with this idea quite naturally of a feature store. And a feature store is effectively a data store, and it can hold features for some given scope of the business. For example, a customer or household, and it's typically at a particular time granularity, so daily, weekly, yearly. It could be at a specific timestamp as well. And there's a few different ways that you can actually store this kind of data. So there's two of the main ones are EAVT and Tabular. So EAVT stands for Entity Attribute Value Timestamp. And what that looks like is something like this. You have your entity column, which is your users. You have your attribute column, which is your actual features. You have your value, which is the value for that particular entity attribute timestamp combination. And then you have the time, which is when it was actually captured. Now, appending new data to this or new features to this is really straightforward because it's basically just adding data to a single table. And because you don't have any schema on the value, you don't have to worry about anything at that time. It's only when you read it that that becomes a problem. However, when you want to actually run your machine learning training on this, you need to pivot this table. And this can be very expensive, especially when done naively on HDFS. There are certainly some great solutions that let you do this at scale very efficiently, but they are not as common. Now, the other approach is tabular, and the tabular approach is basically the format that we want to end up in. So, for example, you've got your customer and date, and you've got your set of features that are tied to each customer date. And then the biggest issue with this one, whilst this is really efficient for your actual machine learning usage, it tends to be a little bit more cumbersome when it comes to adding new features and maintaining this table, because obviously every new feature you add requires a big expensive join and so on and so forth. Now, we went down the tabular path, for better or for worse, to begin with. And to give you a little bit of context on the data center that we were using, we had an on-premise data center. We were often fighting for cluster resources. It was a lot smaller than would have been ideal, unfortunately not in the cloud. And we were using, at the time, Hortonworks 2.5, which meant a very, very old version of Spark, and older versions of Hive and HBase as well, which kind of constrained a lot of the things in terms of performance that we could achieve. So we sort of started with this thing of, if we're going to centralize a feature store, if we're going to build a feature store that lots of different teams can use, we need to have an understanding of what a feature looks like first. So we had this idea of a basic feature library. And a feature library would allow us to have a single source for the feature logic. It would allow us to loosely couple the features themselves from their actual usage, and it would allow us to have all this stuff source controlled. And so we started with this and thought, okay, what can we get from Spark for free to actually implement this thing? And we looked at the Spark Transformer API. So if you're familiar with Spark ML, there's this Transformer API, and you've got all your different estimators and transformers and all this kind of stuff implemented on top of it. And what it does is it basically says, give me a data frame, I'm going to do some transformation, and I'm going to spit out a new data frame. And I'm going to add some extra information about the schema on the output and stuff. So it's basically just a glorified map. And so we took this because it kind of fits into machine learning pipelines. It gives you a lot of niceties around that kind of stuff, and thought, let's see how far we can get with this. So we started with something very simple. It was a very, very, very lightweight OO wrapper around this kind of thing, because most of our users were familiar with Python and basic OO. Not so much the Scala side of things or the functional programming side of things, but our data engineers wanted to use Scala at the time. So we also created these sort of helper functions in here to allow you to generate all the stuff that you need to generate without worrying about how do you implement all these interfaces and do all the stuff that needs to happen for the transformer APIs. And then we also abstracted over date range here. And date range is an interesting one to abstract over because on one hand, it means that our data engineers can basically say, I have full flexibility on how I want to generate big historical snapshots. I can do it in monthly chunks. I can do it over big 6-month blocks. I can do it for a single day if I want to do scoring, for example. But it makes the logic very tedious to implement as a data scientist, or even as a data engineer, really. And so on top of this, we found that avoiding duplication of code became quite an issue with this sort of very naive, simplistic approach to this problem. And the performance of our feature generation actually suffered a lot because of this. It's really hard to know which bits of the code are actually being invoked and what bits should be cached and what bits should be shared and stuff, unless you're familiar with the entire code base in one go. We also noticed that a lot of users were doing something like this, where they'd basically just take some SQL from another system and just spit it into Spark and go, done. And this is great. It's really, really useful that Spark can do this, but it's really, really painful for us if we want to take this and optimize it in any way. And on top of this, it makes things like testing impossible. So we went back to the drawing board. We said, this is too complex to use. There are too many ways that users can make mistakes. And we decided that we needed a higher level declarative language. So we kind of took some inspiration from Spark and from TensorFlow and functional programming in general and said, if we can make the feature definitions a declarative independent thing and then somehow globally optimize these declarations, then we can provide a much better experience. And so we came up with something along the lines of this, where we basically would produce these feature descriptions independent of one another. We would then put them into this feature generator, which would work out an efficient way to put them together and write some Spark code to actually execute these things. And we'd spit out these optimized features. Now, if you kind of squint, this is more or less a compiler. We're basically taking in a set of descriptions, we're compiling it down, and we're spitting out some efficient code. And the main thing that we were doing here is basically optimizing at the domain level as opposed to the level that Spark optimizes at. So the output of this actually becomes the input to Spark. And the idea here is that you've got all your catalyst optimizations and all this kind of stuff for free at the output of what we were doing. Now, the nice thing about this is it allows us to actually centralize all of our optimization logic, and it also lets us transparently improve this thing without the users having to rewrite their code. They've already declared their intent as opposed to how to get the thing they want, and so we can actually work out how to give them what they want and keep improving that over time. So what that kind of looked like is one of those transformers. Rather than just spitting out a single column, say, we could combine the way that these things were computed and spit out multiple columns, which would avoid a lot of I/O, it would avoid a lot of joins and all this kind of stuff. So if you think about kind of abstractly at the optimization level, what kinds of things we were doing without going into specifics, we were doing things to effectively reduce I/O, to share compute as much as possible, and to share caching where possible. Now, this meant that we could do things like exposing interfaces to make smart use of HDFS partitioning, to avoid reading data. We could combine multiple features that read from the same table or the same common aggregates. We could cache these things where we had lots of tables reading from it, all this kind of stuff. So you can imagine with a very, very, very simple example, if we had two features that were just a simple select from some other table, for example, we had a table that had some other features pre-computed by another team and they just wanted to be able to pull them in. In this particular case, we might have select column 1 from table, select column 2 from table as two separate features. The first feature, if you run it naively, will just take in the data frame, which is your base population effectively, and it will spit out that feature. The next feature will then take in that data frame, and it will spit out the second feature, column 2. So what we did is when we pass this into our feature generator, it spits out this optimized feature, which actually kind of combines these two things. And then you basically get a single optimized transformer, which will spit out the 2 columns. Now, this is obviously a very simple example, but these are the kinds of things that we were doing. This obviously reduces I/O. It means you only scan that table once. And when those tables are really big, this makes a huge difference. So we went from this kind of monstrosity of code where we had to deal with all these date ranges and all of this sort of implementation detail complexity to a sort of much simpler version, which basically said, all you need to do is give us the metadata that we care about for this particular problem. Tell us what table you're trying to get things from, and we were able to sort of define aggregates and all this kind of stuff in terms of Scala at this point, and tell us what columns you care about or the pre-aggregations you want on those tables. Now, the thing to notice here is that there's no complex date range calculations. There's none of that stuff that you would otherwise have had to do if you were handwriting it. And on top of that, we basically went and looked at the types of queries people were running and realized that there was a kind of 80-20 rule in play. A majority of the things people were trying to do fell into a few main categories. And so what we did is we actually exposed some interfaces for these categories. And ultimately, we found the most efficient way to execute those types of queries. So for example, here we had a windowed event feature, which was running on our event store, which was basically something that captured things that users had done across all the different data sources. And we said, a lot of people are trying to do events where they're counting instances of things that have happened in this table. And so we basically produced a very simple interface that let them do that without having to worry about how do I optimize this for the partitioning and how do I get the right number of executors and all this kind of stuff. But even in this case, it was still a little bit too much for some of our users, especially some of the more complex interfaces. So we pulled this up into a UI and said, instead of trying to make all of this Scala code or Python code or R code and have 10 different APIs, let's just make it very, very simple. Like, all of this is declarative at this point anyway. And this allows things like feature creation to be done through the UI. We could do discovery of features, which is actually a lot harder in a code base. We could do metadata management. We could do promotion between environments, so dev, staging, and prod. And this is also another way that we were able to then allow users to test their code as well. We tested the interfaces, so we knew that they were correct, and then they were able to test against data and assert that the transformations that were being run were correct before they promoted them into production. And then also on top of that, we were able to define training and scoring sets. So you could go in and basically create your project and say, these are the features I care about for training, and I want these ones to go into production for scoring. And it basically gave you the full data science kind of experience. It got rid of all the boilerplate. And then we decided, OK, this is starting to look pretty nice. People are using this, and it's being successful. And there was a huge demand across the business to open it up to more teams and to allow more features. So we did exactly that. And it turns out that adding more users and features without adding more executors is a recipe for disaster. So we got some inspired user feedback and decided that we kind of missed a really important question along the way here. And that question is more of an organizational question of who pays for this thing. So we looked at cost and we said, OK, does the feature store get a budget of its own, or do the projects pay for their own usage? And if the feature store is getting a budget of its own, how much funding or resource does it get? Like, it's hard to predict these things in advance. Or how much do you determine a fair use policy that meets business goals without users being able to rot the system in some way? And if the projects are paying for usage, what exactly are they paying for? Because we're compiling all this stuff down, making it super efficient and munging it all together. How do we kind of unravel this thing and work out which bit of which code is actually affecting processing? And we kind of found a solution to this by going down a different path, which I'll show you now. So I'm going to show you what I call the null problem. Let's say you've got project 1 that comes along, and they want, at timestamp 0 and 1, customers 0 and 1 for features 1 and 2. Project 2 comes along, and they want slightly different time range. They want an overlapping customer set, maybe from a different part of the business, and they want one of the features the same and another one different. What happens when you actually build this kind of big central feature store is that you end up with something like this. Now, the issue here is that you have this non-overlapping customer sets. You have history ranges that don't exist for certain features. So you end up with a lot of data in this table that's either null or meaningless. It's not used by anyone. And so we thought, OK, if we're going to do this, we need to work out how to optimize this process. So we looked into it a little bit more. We started by looking at how many users were actually in our total data set. And it turned out there were 30 million, which is about 7 million more than the total number of people in Australia somehow. Now, we had two customer sets in this case, for example, of one customer set 1 and customer set 2. And typically what happens is your set of features are tied to the source systems that you're getting them out of. So, for example, in customer set 1, you might have features A and B. In customer set 2, you might have features C and D. And so if you want to actually use features across all of these customer sets, you end up only actually having the overlap of these two things as reasonable data to use. So say in this case it was 10 million. And what we found is that a lot of projects were trying to target very specific things. So they were saying, you know, we want to model postpaid churn and we want to try and reduce that. And so that ends up being even smaller again. Maybe it was in customer set 2 and then only part of that is defined in both. So what you end up with is this kind of final overlapping bit. And so what that looks like is roughly this, where what the projects actually need in an individual basis is about 2 million. And what we were trying to do was generate this thing with 30 million customers for all of time. So we did some quick back-of-the-envelope calculations and found with, say, 30 million users, 365 days for 2 years, for, say, 1,000 features, a union across all of the projects, that it was about 22 trillion data points. But per project, when we multiplied out all the numbers, 2 million by 365 days by 2 years by 300 features, it was actually only about 500 million data points. And this is a lot more tractable problem, especially, as I mentioned, we had a fairly small cluster. So this kind of thing becomes a lot more simple. Now, we had this crazy idea that rather than building this big centralized table, what about if we try and generate these training data sets on demand when people actually want them? The idea here was that it would remove this enormous engineering cost of building and maintaining this kind of monstrous centralized table that is actually mostly useless or mostly null. And it would allow teams to get started on the modeling much faster. If we're going to do this, we worked out we need to make this thing super efficient. So we started looking at a whole bunch of different ways to speed up our feature table snapshot generation, and kind of started with the DAG, because it turned out that this was our biggest bottleneck. So as I mentioned earlier, we went with this feature transformer interface and kind of built this thing on top. And when we spit out multiple things, we might have multiple stages that take in the previous feature as input and spit out more columns and so on. But what actually happens when you do this in Spark is that you end up with a DAG that looks like this. And you can kind of see the problem, hopefully, in that you've got this big linear dependency join going down the left-hand side. So what was happening is that we were calculating all of our features along the right-hand side and getting all of the actual values, but then to make it this big centralized table, we had to kind of wait and do this big linear join where we were putting one next to the other. And so what we did is we said, OK, let's see if we can optimize this by pushing things out to the leaves. So each one of the features will generate independently, and each one of them will have only the customer set and date range that they care about. And then rather than doing this big left outer join, we're going to do a full outer join and have this in sort of a logarithmic fashion merging down. Now, this is still a lot of work, obviously, but what it means is that we can parallelize this thing, and we can actually get our executors working together on actually getting this thing done quicker. And it's only sort of when you get to the bottom down around here that it starts to degrade to the performance that we had in the linear version. So if I were to show you what this looks like in terms of, hand-wavy kind of optimization charts, the blue one is what happened before. So our executors would shoot up to 100% utilization, and then they'd drop down really quickly as they got to that final linear join. But when we changed it to this logarithmic merge, it shot up to 100% and stayed there a lot longer before it dropped down to a much lower percentage. And as a result, we ended up finishing our jobs a lot quicker, which is the desired effect. Now, we also had some general Spark performance tuning. We did a lot of things here, but one of the biggest things of note is something that's actually fairly obvious probably to a lot of people in this room, but I'll just point it out again in case. And that is the way that parallel processing works. So if you have, say, 30 tasks that you want to run, and you only have 15 resources to actually run it on, then assuming that each resource takes the same amount of time to compute, say time t, that first section will take time t. Then the 15 resources will pick up the next 15 tasks, and that will run again, and that whole thing will take time 2t. Now, what we noticed is that we had these default stages of 200 tasks. We actually also had this artificial limit put on by the tech ops team of 200 resources. And they had their reasons for this, but it turned out that we were ending up in this situation where we had 196 things being calculated in time t, and then 4 things calculated in time t. Now, the problem with this, obviously, is that when you have a compiler like we did that basically put all of these very expensive operations in, that time t becomes enormous. So we were saying, this might have been 2 or 3 hours. We were doubling that for no real reason other than the fact that we were missing 4 executors or we had slightly too many shuffle partitions. And so obviously we reduced this, or we added some more executors, and this basically solved that problem for us. So always look out for this kind of thing. Especially to people who are fairly new to Spark, this looks like it's actually progressing really fast, but you need to be careful of that last bit. And the other thing that we did, as I mentioned, we started on Spark 1.6, and this was obviously fairly slow comparatively to some of the newer stuff, and we migrated to 2.2. Now, there's a lot of reasons to migrate, but one of the biggest one that we found was that on a lot of the features we were calculating, it was up to 17 times faster. So this is pretty substantial, especially when we're talking about sort of fairly small cluster sizes. This is enormous. But more importantly than that, we actually found that the stability and logging was so much better in 2.2 that we were working a lot quicker. We weren't running into these silly edge cases of, we wrote an awk file and it would just crash for no good reason. We didn't run into those issues anywhere near as much anymore, which meant that we could actually iterate a lot quicker on our solution. So in terms of the relative performance gains, obviously the hours column is a function of a lot of different things like our cluster size and all this kind of stuff. So don't worry too much, but the relative difference is somewhat meaningful. And you can kind of see these small batches when we were trying to calculate small number of features over small history initially with that kind of handwritten approach where people weren't optimizing it very well. Would take maybe 6 hours, and then if we tried to do something a little bit bigger for 3 months, 250 features, it might take most of the day. And then if we tried to calculate something really big, it would literally never finish. It would either crash or it would run out of time. With the declarative approach, we managed to drop this by maybe 30 to 40%. And this was without any of the optimizations, which was quite nice. And then finally, once we went through and did all of those other optimizations I spoke you through, the logarithmic merges and all this kind of stuff, and combining the table reads and the IO and the caching and all this kind of stuff, we managed to get the snapshot tables down to be incredibly quick, down to minutes. So this is an enormous gain. These are projects that would come along initially and basically say, I have a month to get my features ready and create my table. And now they can come along and basically say, in a day, I'm going to have something that I can start using. And then obviously you can see here, we could kind of generate the entire large tables that they wanted of, say, 400 features or whatever, over the 2-year history, all that kind of stuff, fairly quickly. Now, again, features are probably not the best thing to kind of compare in benchmarks because they differ a lot in terms of complexity. So 250 features here may not seem like a lot if all you're doing is kind of doing very simple calculations on, say, a click stream. But these were very, very expensive aggregations in general. So I was pretty happy with the outcome of this. Now, for takeaways, naive centralization of this feature store is really hard and expensive. It really pays to work out your usage patterns before you go too far in. So we kind of realized after we'd done a lot of work that we could actually get rid of a lot of the complexity we were trying to deal with by not actually managing a big central store, by just generating these snapshots. Now, working out how to manage resources, resource usage, and cost early on is really beneficial. Getting the business and the technical side aligned on this is really important. And as I mentioned, constraining the surface area of the optimization problem is essential to get anywhere on this. If you think about the kinds of things you can do with feature engineering, it's literally an infinitely big problem. So if you can constrain what you're trying to do here and the types of things you're optimizing, that solves that problem in a lot of ways. We actually offered the ability for data scientists and data engineers to still go in and write their features however they wanted, as well as all these sort of interfaces we exposed. And then they could still select them through the UI and everything, so it was all there for them. Now, I think probably the biggest thing here is if you're building this kind of system, every company seems to build their own thing because there's nothing kind of open source that does this well that I'm aware of currently. is that features should be independently declarable with their own metadata and everything, but should be globally optimized. You don't want to pay the cost of nice interface for performance. So yeah, the more declarative the interaction as a result, the more you can do for your users transparently. Thank you.
Thank you, Cameron. That was very nice.